Hey everyone, my name is Jeffrey Johnson and I'm from Boise State University. This presentation reports on what I think are some very cool observations of volcano sounds made using conventional video cameras. I'm going to argue that there is some very strong potential for understanding the volcano infrasound source and the effects of crater geometry using cameras, hence the usage of a new term that I refer to as volcano opto-acoustics. The data I'll be presenting come from Yasur volcano in Vanuatu. My introductory slide here shows a typical explosion at Yasur along with an infrasound record from a sensor located at the red circle, some 300 meters from the vent. The yellow waveform shows pixel brightness values queried at the location of the yellow star. What should be apparent is the similarity of these waveforms, suggesting that cameras and microphones have the potential to record the same phenomena. I'll come back to this slide later, describe how it was created, and show it as an animation. Yasur is a fantastic laboratory for studying volcano infrasound. It is one of about a half dozen open-vent volcanoes worldwide with lava lakes. It is located in the Vanuatu archipelago and has incredibly easy access once on the island of Tanna. Eruptive activity can be relatively safely observed from various points on the crater rim. The volcano holds two active craters with numerous vents, each located about 200 meters below the crater rim. The view shown here is of the south crater, and the people in the foreground are standing at the location where our GoPro video data were collected. This explosion, for instance, generated a 600 Pascal 1 Hz pulse at 300 meter distance, which was enough to shake the tripod. It is typical and one of the many explosions occurring from both events during our period of observation. Here I'm showing the waveform for that explosion within a 3-hour example of Yasur infrasound. The infrasound transients, or explosions, are noticeable as spikes, and some have amplitudes in excess of 1,000 pascals, while the tremor, which is continuous, regularly exceeds 50 pascals peak to peak. For reference, the sound level of a typical conversation is only around a few millipascal, some 1,000 times lower in amplitude than the pervasive and continuous, yet non-audible, infrasound tremor. So let's look at the single explosion featured in the helicorder record in more detail. This video shows time-synchronized infrasound indicated by the moving circle symbol. Location of the infrasound recording site is the red triangle. As expected, this explosion event has a high-amplitude compression, followed by some oscillations. It's a rather complicated coda, and these oscillations have been previously attributed to crater resonance effects. Interestingly, the trailing oscillations are also visible to the naked eye. Playing this video again, but more slowly, you may be able to see multiple pulses of cloud condensation that propagate from the south vent outward. Enhanced video, exaggerating infrasound band fluctuations in video brightness, emphasizes these pulses and their general radial propagation. Now, in an effort to see how these pulses relate to infrasound, we decided to analyze the video-derived time history of pixel brightness. Following is the processing I perform for the indicated pixels near the yellow star. First, we convert the RGB video to grayscale imagery and perform a Gaussian spatial smoothing filter. A smoothing filter of about 10 pixels corresponds to the yellow circle in the previous video. Smoothing provides a convenient means to dither the 8-bit color values and give increased pixel intensity resolution. Next, we filter the pixel's color evolution in the time domain. In this talk, I picked a filter band between 0.4 Hz and 5 Hz because it appears to be the primary band where Yasur's most intense infrasound is recorded. Next, we perform a simple polarity reversal. Brightening, which is indicated by increasing color counts, is flipped negative. This is done because of our hypothesis that relatively low pressures, due to the rarefaction pulses of the infrasound, should facilitate condensation of water vapor in the atmosphere. This should cause the cloud to brighten in the video. High pressures have the opposite effect. The cloud diminishes and it gets darker. Finally, we overlay the inverted pixel brightness time series with the recorded time synchronized infrasound from near the same locale. Note please that the infrasound has been filtered in the same 0.4 to 5 Hz band. When I first did this analysis, I was very impressed by the high degree of correlation of infrasound and video-derived infrasound. But I was also concerned that it might be a one-off result for a specific explosion. So then I started to look at more explosion events and was excited to see the similarity for virtually all events. The red box here corresponds to an 11-minute GoPro video for which there are 6 explosions exceeding 150 Pascal peak to peak. These infrasound waveforms are shown in the left panel in black and closely relate to the video-derived infrasound shown in color, overlapping with these waveforms. Parenthetical numbers here indicate normalized cross-correlation coefficients, which are quite high for the 20-second windows. Notably, the tremor both before and after the explosions also shows a high degree of correlation, indicating that the cloud condensation is detectable even for tremor. In fact, good correlation is evident for signals as low as about 5 to 10 pascals in amplitude in this case. The relationship between pressure and pixel intensity is remarkably linear up to amplitudes of several hundred pascals. Here we have regression lines plotted through a comparison of the data. A single pixel of brightening corresponds to somewhere between 40 and 80 pascal pressure drop. Thanks to neighboring averaging of pixels, we can detect pressure changes that are far smaller than this. The relationship between recorded infrasound and pixel intensity is also clear in the frequency domain. Here we are looking at spectra for the entire 11-minute GoPro video and querying pixel intensity near the infrasound station. This time period shows spectral peaks evident at 0.6 and 1.5 Hz. Based upon these observations, we became interested in how far we can push the video to extract spatially distributed infrasound. The premise is that regions within the field of view showing pixel brightness variations in 0.4 to 5 Hz band potentially correspond to infrasound. Mapping the variance of filtered video shows regions where infrasound might be detectable. These high variances correspond to regions where there is ambient plume. In other words, no pre-existing cloud means limited capability for seeing the infrasound. Examining these time series sorted by distance from explosion also gives a sense for distance time move-out. We can query each of these locations independently to see what the time history of video-inferred infrasound look like. Examining the waveform variations along a transect not only gives a phase velocity, but shows potentially interesting evolution in pressure waveforms that suggest topography-induced interference effects. I'd argue that the waveforms between points numbers 7 and 33 show promising infrasound information. The high degree of correlation between video-derived infrasound and actual infrasound at point 21 is not surprising, because that is where our infrasound station was located. Spectral content of the video-derived infrasound shows fairly consistent peaks for this event over much of the field of view. Peaks at 0.8 Hz and 2.5 Hz are suggestive of integer overtones reminiscent of an open-closed pipe-like resonator. Subtle differences in spectra are evident along the transect, but the peaks are consistent even if phase is not. So now we come to the work moving forward. We are currently in the process of trying to understand whether cameras can be used as reliable, spatially distributed infrasonic microphones. Toward this end, numerical modeling of the acoustic source using integrated topography will be illuminating. Fortunately, we were able to acquire good accuracy topography of the crater geometry through quadcopter structure from motion flights. Here you are seeing a high-resolution map decimated down to 1 meter resolution. Despite fumey conditions and one Mavic Pro lost to the lava lake, we are happy with the reconstructions, which included visibility all the way to the crater floors. The GoPro video camera was located at the yellow circle, and the dashed lines shown here represent the camera's field of view. Our infrasound station is indicated with the red circle, and profile slices will be calculated along the transect labeled A because it is orthogonal to the camera's look direction. We've run models with sources positioned throughout the crater's bottoms, indicated by the blue points, but the only ones we're prepared to show right now are from the large blue circles in the north and south crater bottoms. The perspective view here matches the view from the GoPro camera site, and the topography and draped orthophoto come directly from the structure from motion analysis. Contour intervals are plotted at 25 meter, and slant distances are indicated in the parentheses. Once we start the animation, you'll note that reds and blues are associated with positive and negative pressure polarities, respectively. Interference due to crater wall echoes and diffracted waves are evident. Accurate topography is a critical input to the 3D acoustic propagation code used to produce Green's functions for the different craters. Here I show a vertical slice for an acoustic source, which is a delta pressure pulse function bandpassed between 0.4 and 5 Hz. This source is meant to represent an impulse response. For comparison, here's the acoustic wave propagation model run for a source put at the bottom of the north crater. Examining the output waveforms along transects reveals a spatially dependent waveform evolution and frequency content that is similar to that extracted from the video. Similarity of some of the spectral peaks point to replication of crater resonance in the numerical models. We are currently evaluating the differences between modeled and optically derived infrasound. A partial list of explanations to consider include that video-derived infrasound is not as accurate as we want it to be. Further work with coincident infrasound sensors in video would be most helpful to address this. 2. Our various modeling assumptions, as well as the DEM or atmospheric structure assumptions, need improvement. 3. There is uncertainty in the nature of the source time function. Note that we don't expect the time series to match in our modeling with our real data, but we believe that we should be able to evaluate the spectral response and use this to determine the source spectral content. And finally, 4. Precision vent location matters. Yasur's crater bottoms are large and have many vents distributed over significant area. This last point definitely merits consideration. As mentioned in a previous slide, we've now imposed dozens of sources at the bottom of Yasur's craters and calculated Green's functions for each. Although I won't be able to talk about these results right now, I will end this talk with a brief video highlighting the complexity of the source distribution at the bottom of the south crater. It should be noted that the Green's functions for each of these vents is affected uniquely due to its position related to the steep-walled topography. I hope you're still listening because I want to credit my co-authors. 2 of them, master's student Brian Rosenblatt and research professor Jake Anderson, come from Boise State University and have been instrumental in the sensor development, data collection and analysis, and in helpful discussions about volcano acoustic resonance. Leighton Watson is from University of Oregon and is a crater resonance specialist who is developing fast numerical models for ascertaining crater responses. Ki-Hoon Kim from Lawrence Livermore National Laboratory is the engineer of the 3D finite difference code, which is used by many groups within the volcano acoustics community. Finally, Thomas Boyer is our local partner in Vanuatu and is a specialist in that volcano's eruptive behavior. Without him and local guide Jackson Lakapas, none of this work would have been possible.